Hello and welcome everyone to our deep dive on reasoning to learn from latent thoughts. I'm thrilled to host this conversation because it's a topic that seems both futuristic and immediately relevant for leaders in business and tech. Let's kick this off by introducing our 5 experts, each with distinct perspectives.
Thanks for having me. I'm a technical lead focusing on language models and large-scale pre-training, and I've been experimenting with novel ways to embed latent thoughts into data pipelines.
Great to be here. I'm a chief strategy officer at a mid-sized tech firm, so I'll be bringing in the business angle, especially how these iterative techniques might reposition entire product lines.
Hello, everyone. I'm a researcher specializing in latent variable models, so I look forward to discussing both the mathy side and the practical engineering challenges.
Glad to join. I come from a data science background at an enterprise-scale retailer, so I can share some real-world insights about deploying these methods in a high-volume environment.
And I'm the last in line, but hopefully not the least. I'm a software architect, quite hands-on with advanced LLM fine-tuning and synthetic data generation. I'm excited to dig into the details of these methods.
Fantastic. Let's begin with the big idea behind reasoning to learn from latent thoughts. Expert 1, would you mind describing what's going on under the hood?
Sure, the essential concept is that human-authored text is just the tip of an iceberg. People produce a final statement or result, but there's all this hidden reasoning that leads up to it. The approach says, hey, maybe we should train language models not just on the final text, but also on the underlying or inferred thought processes. The result is that models learn more efficiently because they get exposed to an expanded, more detailed representation.
Right? So, from a business leader's standpoint, we could see real cost savings in data-scarce contexts. Companies often spend heavy budgets on curated text corpora. If we can enrich or bootstrap those corpora with synthetic reasoning, then we're effectively multiplying the value of existing data.
Precisely. Let me give a mini technical deep dive. In math terms, we're moving from modeling P of x, where x is the observed text, to modeling P of zx, with z as the unobserved chain of reasoning. Then we try to approximate Q z x, the posterior distribution of these latent thoughts. If we do it well, the model soaks up more nuanced knowledge from each sample.
That's interesting. Building on that, we trialed something like this for a partial domain, like financial forecasting scripts. Normally, the text is just final conclusions, but the underlying financial models have step-by-step logic. Once we embedded the intermediate steps as latent thoughts, the forecasting improved by 10% on internal A/B tests. It was not trivial to implement, but the payoff was exciting.
Yeah, implementing is the key. We found that simply stuffing chain of thought text into the raw data wasn't enough. We had to keep the chain of thought separate as a latent space. So you feed the model, chunk of text, chunk of reasoning, chunk of text, chunk of reasoning, etc. This let the model treat the thought content differently from the observed text. It's a bit like teaching a student to show their work on math problems. They learn better, and the teacher, the model, sees the hidden steps.
I love that analogy. Show your work. Actually, it reminds me of that old Einstein quote, imagination is more important than knowledge. In a sense, we're giving the machine some imagination about the steps in between.
Ha, indeed we are, though I'd be careful about calling it imagination. It's more structured than that, like systematically enumerating plausible hidden steps. But you can almost think of it as a new dimension of data.
Yes, but there's a big challenge. We must not degrade data quality with random or erroneous thought expansions. So we often do multiple sampling attempts for these latent thoughts and re-weight them by their likelihood or utility. It's somewhat reminiscent of a policy improvement operator in reinforcement learning.
Exactly. The paper mentions an EM, expectation maximization approach, bootstrapping latent thoughts, or BALT. If we produce multiple candidate reasoning paths for each example and pick the best, iteration by iteration, we gradually refine the model's posterior. Each iteration yields a better model that in turn creates better synthetic data.
That's neat. In business terms, you might say we start with some baseline text, generate reasoning expansions, train a better model, then the better model yields better expansions, and so on. So data-limited industries, like specialized medical or legal fields, can effectively amplify a small corpus.
Yes, and the cost savings can be huge. Imagine you're trying to build a domain-specific medical language model, but you only have a fixed set of clinical notes. By synthesizing reasoning like, the patient's symptoms imply X, so we suspect Y, leading to Z, the model might learn more robust patterns with fewer real documents.
That's a compelling use case. Now, there's always a catch, right? Could we talk about the challenges or risks?
Sure. One catch is mode collapse. If your synthetic latents become repetitive or are generated poorly, the model could spiral into producing cookie-cutter text. That's why it's crucial to maintain diversity and correctness in the latents. Another is the potential for data drift. Your expansions might misrepresent the original domain if not carefully managed.
From a strategic perspective, companies might also worry about compliance and interpretability. If you're creating new text, these hidden reasonings, you must ensure they don't produce misleading logic or bias. Regulated industries might demand an audit of exactly where these expansions came from.
Right. Or you can think of it as the system is forging part of the data. That's okay if it's consistent and leads to better performance, but we need robust guardrails. Automated alignment checks, or at least random sampling for correctness, might be needed before final acceptance.
Let me share a real-world story, kind of a cautionary tale. At our retailer, we tried generating latent reasons behind product recommendations. The idea was that the model would see the steps, like, if user is interested in brand X, also show brand Y. But we ended up with some bizarre expansions that included inaccurate competitor crosslinks. Our internal docs ended up referencing deals that never existed. We had to clamp that down quickly.
That's a prime example of the synergy versus risk trade-off. Another dimension is compute. Generating multiple latent expansions can be heavy. You might need more compute at the inference stage if you do it repeatedly, or more resources at training time to handle the bigger data set.
So we have potential ways forward, but it's not a trivial fix. Now I want to pivot to a deeper technical conversation. Expert 3, how do you handle the posterior sampling for the E-step in that EM approach?
Great question. In the simplest approach, you sample K candidate latents from Q of Z XMT at iteration T. Then you re-weight them with importance sampling, WK equals P of Ziv K X XMT. This yields a better approximation Q for the next iteration. The model then trains on those chosen latents. It's reminiscent of importance-weighted autoencoders, if you're familiar with those.
Yes, and the name of the game is scaling. The more candidate latents you can sample, the better your chance of picking a truly helpful latent. But hey, that increases your compute cost. It's a classic 80-20 scenario. 80% of your improvement might come from the first few samples, but that last 20% improvement might require a big compute ramp-up.
Right, so from a business side, you weigh the cost of extra sampling versus the gains in model performance. If your margin is high enough and the domain is valuable, you might invest in generating thousands of latents. Otherwise, you do fewer. This is basically an ROI analysis on data efficiency.
I see your point, Expert 4, and I'd add that for smaller startups with limited data, the ROI can be significant. Even a modest improvement in data efficiency might determine whether they can release a new product on schedule. It's not just about giant enterprises.
That's a good clarifier. Let's talk about advantage for companies beyond cost. Are we seeing any strategic differentiators, like beating competitors by gleaning better reasoning?
Actually, yes, there's the competitive edge. The model that can reason better with limited data can be more agile. In an M&A scenario, for example, a company might quickly spin up domain-specific capabilities using only the doc sets from an acquired firm. I recall a health tech that integrated another clinic's patient data. They used something akin to latent expansions to unify the different record systems. While the details are proprietary, I suspect it's basically this approach.
That's cousin to the looped transformer approach, or chain of thought distillation, but now done systematically across the entire corpus. Think of it like rebuilding an engine while you're driving the car. You're constantly refining your own synthetic data generation pipeline, all while the final product has to keep serving users.
Quick contrarian note. Not everyone believes reflecting the intermediate chain of thought in text is always beneficial. Some argue that the best knowledge emerges from hidden state representations, not from explicit text expansions. But the experiments we've seen do show promising results, so it's not just academic fluff.
Right. And maybe the sweet spot is a hybrid, where some steps remain in hidden states, while certain structured expansions get surfaced to steer the model. Just enough to get the benefit, but not so much that you open the door to confusion or user misinterpretation.
So it's a balancing act. Let's devolve into one more technical deep dive. Expert 1, can you talk about how the model actually references these latent tokens during inference?
Certainly. In practice, you might label the input chunk as "that's start of latent," end of latent, allowing the model to differentiate between raw text X and latent text Z. Then, at generation time, you can either feed the model an instruction that tells it to produce hidden latents in that bracket or continue in raw text mode. Using a random coin flip approach during training helps the model learn both PZX and QZX. In inference, you can do a chain of thought in the latent space, sampling from P of X prime Z to X. Or for few-shot prompts, you might demonstrate how to produce reasoning in that special token block. The result is the model can reason internally before producing the final user-facing output.
And performance improves notably because the model has practiced generating those intermediate steps, so it's like it's been trained to internalize reasoning. Also for tasks like math or coding, that's very powerful.
We saw a 25% accuracy jump in a domain-specific problem set once we integrated latent thoughts. It was actually more robust to prompt variations too, so the benefits weren't just raw accuracy, they included stability.
Our audience might also wonder, is this the future of large language model training?
From a business vantage point, I see it as a major direction. Data is going to run out if we keep scaling at our current rate. So either we pause scaling or we figure out ways to amplify limited text. That's exactly what these latent expansions do. It's a data multiplier.
One small comedic angle here. Ironically, we're helping the model think out loud so it can later do better silent thinking. It's like teaching a toddler to speak their thoughts so eventually they can do mental math. Honestly, it's kind of endearing and maybe a little spooky.
Endearing and spooky. That's the tagline. Let's do a final rundown. Each of you share one final tip or caution for leaders who might want to adopt latent thought models.
My tip: ensure process diversity. Don't just generate one chain of thought per document. Sample multiple attempts. Keep the best ones. Complexity fosters better learning.
Mine, watch the business ROI. You may need extra compute or experts in advanced ML. Be sure it pays off strategically.
Understand the technical constraints. If you skip reweighting or sampling properly, your expansions might degrade the data. Good methodology is non-negotiable.
Absolutely. And implement robust QA checks. Run small-scale tests to confirm your synthetic latents aren't going off the rails. Otherwise, you might store big volumes of flawed expansions.
Finally, keep an open mind about data biases. If your base corpus is skewed, your expansions might amplify that. Make sure you integrate fairness guidelines up front.
That's a wrap, folks. We tackled everything from data efficiency to EM algorithms, from business ROI to the engine rebuild analogy. Thanks to all our experts for a lively discussion full of deep insights, cautionary tales, and yes, a pinch of humor. Until next time, stay curious, everyone. Actually, I can't resist. Before we truly sign off, I'd love for us to do a part 2 and dig even deeper into implementation details and broader business opportunities. Is everyone game for a bit more discussion?
Absolutely. Let's keep it going. So, from an engineering standpoint, the first big question is how you integrate these latent thoughts into your normal training script. Typically, you'd chunk each training document, maybe a few paragraphs, then generate or attach the chain of thought snippet. You mark them clearly with special tokens, as we discussed. But you also have to manage your sequence lengths carefully so you don't blow up GPU memory.
Right? And for business leaders, that means you might need to re-architect your data pipelines. If your corpora were purely linear text, you have to insert an extra pipeline step that calls your model to produce these expansions. That's an investment in both tooling and staff training.
Precisely. And the biggest technical detail is chunking. Some folks do a random chunk size distribution with a mean of around 8 sentences, so you can systematically pair each chunk with a latent snippet. You also do random context windows to ensure the model doesn't overfit on just one style of chunk.
We used to separate everything into 1,000-token context. Then we realized we were missing cross-chunk reasoning. So we ended up with a sliding window approach that overlaps the contexts by 20%. That gave the model a sense of continuity. Might cost more compute, but oh well, the results were worth it.
Building on that, you also want a stable training schedule. Sometimes you do 5 or 6 epochs over the newly augmented data. We tried a single epoch at first, but the model didn't fully absorb the latents. Doing multiple epochs, or even rewriting them in mini batches that mix old raw text with these newly minted expansions, gave us better consistency.
So it's not just a plug-and-play situation. This is definitely more involved. Expert 2, from a leadership angle, how do you talk to your CFO about this sort of extra cost or time?
That's the million-dollar question. I usually frame it as, we're paying an upfront complexity tax to double or triple the efficiency of our data. If the CFO only hears, we want to tinker with the data pipeline, that's a no. But if they see that we can reduce the total data purchase or expedite next year's model rollout, it's a yes. We also highlight intangible benefits, like staff learning cutting-edge skill sets, which are valuable assets.
Another pro tip is that after each iteration of latent generation, you can store that synthetic data in a separate dataset. Then you can run simpler offline checks or domain-specific validation to ensure it's not going haywire.
Exactly. Also, the overall objective is to combine generative sampling with a re-ranking approach. If you can, you do multiple forward passes to gather candidate latents, then use a re-ranker, maybe a smaller model or a heuristic, to keep the best expansions. Think of it like a little dance. You generate, you filter, you only train on the filtered expansions.
We used a latent aggregator that assigned partial scores for correctness, coherence to domain constraints, and diversity. Each dimension had a weighting, so we ended up with a final combined score per latent chain. That made the pipeline more robust.
Yeah, we did something similar for a manufacturing use case, tying each latent chain to a set of operational constraints. Heck, part A can't go into part C, that sort of logic. Our aggregator would quickly discard expansions that violated mechanical feasibility. It was an engineers have final say approach. But the payoff was a way more consistent model.
Great real-world examples. Now let's pivot to advanced business applications. Suppose a company's adopting this for recommendation systems, or even for supply chain optimization. Where do you see the biggest wins?
I see huge potential in supply chain, actually, because supply chain data can be limited or incomplete. Generating these chain-of-thought expansions about why item X might be delayed if route Y is congested can enrich the data. That leads to stronger predictive models and cost savings on logistics. We're talking about real bottom-line improvements, maybe 5 to 10% in shipping efficiency. And don't forget your BFSI. Banking, financial services, and insurance are all about risk models that normally require huge specialized datasets. If we can augment the transitions between variables, like customer credit rating implies X, which implies Y exposures, we can refine risk analysis. That might yield more accurate loan approvals or better fraud detection.
In e-commerce personalization, we can generate hidden reasonings that help the model connect the dots between user interests. Instead of just seeing user clicked item A, so maybe they'll like item B, the latent expansions might note because brand loyalty to A typically implies interest in brand C as well. That was precisely the scenario we tested in my previous role.
This is so cool. Now, let's toss in a sprinkling of humor. Expert 3. Do you ever worry we're basically building a super intelligent system that can write its own diary entries, then read them and become unstoppable?
Well, I find it funny, and maybe a bit terrifying, that we're effectively letting the model train on its own imaginary friends' diaries. But unstoppable? Possibly unstoppable at generating more text. Let's just hope it's not unstoppable at reorganizing our entire supply chain, unasked.
I'll keep my fingers crossed. So as a final pass, can each of you share an unexpected or contrarian insight about these methods?
Sure, mine is that bigger is not always better. Sometimes smaller LMs can see dramatic improvements from latent expansions because they need that reasoning even more than large models do.
I'll say that we're all raving about data efficiency, but be prepared for a plateau effect if your domain is super specialized or messy. The expansions might start repeating, limiting gains.
My contrarian take. Textual expansions might not be the endgame. We could see hierarchical reasoning codes that never appear in text but still speed up learning, like a hidden graph structure behind the scenes.
I'll propose that if you fail to integrate domain experts in the loop, your expansions might become nonsense. So fancy math alone doesn't solve domain complexity. Human curation helps.
And I'll throw in that some companies might prefer end-to-end black box models for simplicity, ironically ignoring the potential clarity from explicit reasonings. So we might see pushback from purely end-to-end folks.
Fantastic perspectives. We've gone deeper on the technical side and showcased real business angles. I think we can wrap up part 2 with that. Thank you all. This has been an incredible conversation on bridging the gap between hidden reasonings and strategic advantages. As always, stay curious and keep thinking, whether silently, out loud, or somewhere in between.